Welcome to another lesson. In this episode, we're going to be taking a look at furthering our understanding of inhomogeneous linear equations. On Monday of this week, we looked at the materials in lesson 19, which were covering sections 4.1 and 4.2, which were basically showing you how to solve an inhomogeneous linear equation using one of two techniques. You either used what's known as method of undetermined coefficients, or if the right-hand side or the forcing term of the differential equation can be viewed as an exponential, either real or complex, meaning it involves sine, cosine, or exponentials in some way, then you could use something that we called exponential response. So most of our work in class on Monday was covering those two techniques. I do want you to know that even though I didn't post a lecture video on Monday, there are lecture notes here. And there are videos. It's videos I already had prepped for class. Inhomogeneous equations, method of undetermined coefficients. You should also take a look at the two complex method videos, which are exponential response. So it goes over those two formulas. And then even this topic, variation of parameters. This is not a topic that I am going to lecture over. It's not in your textbook either. However, I do encourage you to watch this video. And after watching this video, there is one question about this on the Maple quiz for this week. But our goal today is to focus on the phenomenon associated with beats and resonance. So these two videos are going to be the important ones, but I'm going to take you through actual lecture today because I feel like there are several important things to highlight in our discussion today. And we'll bring in a couple of Maple files as well as we're going through this. All right, so our topic for today is defined as beats and resonance, and we've been hinting at these ideas for a while in various forms. I want to start off with just make sure we simply understand what's going on here. So I'm going to kind of read this with you and talk about some things. We're going to be talking about the physical phenomenon of resonance. You're probably familiar with this idea if you've ever seen someone with a glass full of water. They'll maybe wet their finger and then run their finger around the rim of the glass, and it creates this kind of humming, vibrating sound. That is resonance in play. It's the topic we're going to be discussing today in play. Soldiers are taught when they cross over a bridge to break cadence so they don't all stomp at the exact same frequency. That could cause the bridges to collapse, believe it or not. If you've ever seen something called the Tacoma Narrows Bridge, that's also a part of this as well. I'll talk more about the topic of resonance and show you a couple of videos in Friday's lecture. But we are going to introduce what's called pure resonance today. Pure resonance doesn't really exist because it assumes the lack of damping. And we don't get any undamped situations in the real world. There's always some form of damping. So you never get a truly infinite response like we're going to see theoretically today in the work that we do. But I'll show you some examples of resonance in practice in Friday's lecture. The best example, and it's the idea I want you to have cemented into your mind today, is this picture that I have below of a swing set. So you can think of this in a couple of parts. The person that's pushing on the swing set is acting as the input. And then the person swinging itself is the system that the input is affecting. So from a differential equation point of view, y double prime plus omega naught squared y, this is the swing set. And then in today's lecture on the right-hand side, we're going to have a cosine omega 1t, which you could think of this as the person that pushes the swing. This is called the input or the forcing term because it forces the system to respond to that input. Think of it this way, if the person pushing the swing weren't there and you kicked off, right? You kicked off the ground, that's the initial conditions of the system. It's like where you were when you kicked off and how hard you kicked off. That would set you into motion and you would just swing back and forth as long as you weren't trying to manipulate the swing or anything like that. You would just swing back and forth in a oscillatory fashion. And in the absence of damping, whatever your initial kickoff, the energy supplied by that would give you a certain amplitude of oscillation. You would just maintain that amplitude of oscillation for all time. But if I wanted to, as an outside observer, push you, then one of two things can happen. If I push you right at the exact moment that you come back on your swing trajectory and you're about to head back down, and I push you as you're about to head back down, well, then I'm adding a force to your force in a constructive manner, and that will increase the amplitude of your oscillation. If, on the other hand, I try to push you as you're coming back toward me, then that's a destructive form of interference, which would then ultimately decrease the amplitude of the resulting oscillation. So we have two different possibilities here. We have a constructive interference input, which is going to increase the amplitude of the oscillation, versus a destructive interference input, which would decrease the resulting amplitude of the oscillations. And it's very important to understand when each of these happens mathematically. So the basic problem that we are faced with today is this one. We're going to let omega 1 be the frequency of the input, meaning the frequency with which the person on the outside is pushing the swing. And we're going to let omega naught be the natural frequency of the system. It's just naturally the frequency you would oscillate with if you were just swinging alone. What I'd like to do is solve these using some of the techniques that we described in Monday's lecture, and then talk about what the system response looks like in terms of omega 1 and omega naught. So we want to solve this differential equation. And immediately, I want to remind you of exponential response from Monday. The thing I have on the right-hand side, I'll call this f of t. E to the I omega 1t is cosine omega 1t plus I sine omega 1t. And you can see that the forcing function f of t is part of this complex exponential. So I'm going to call this complex exponential fc of t to describe it as being the complex version of our forcing function, f sub c, f complex. So remember, the way that we solved this was we complexified the original model, and I replaced the variable y, since y is a real variable here, with the variable z, which is a complex variable. And we replaced the real forcing term f of t with the complex forcing term e to the I omega 1t. With the realization here that the real part of fc of t is equal to the function f of t that was our input. So this is exponential response. The way that this works is, if you take a look at the roots here of this equation, the characteristic equation P of r is r squared plus omega naught squared. If we set that equal to 0, then we can see that the roots are plus and minus I omega naught. And so because alpha, which is alpha is omega 1 here, is the frequency of our forcing term. It's the value here. It's the frequency of the forcing term. Since it is not equal to plus or minus I omega naught, then we're in case 1 from Monday's lecture, meaning that our solution to this, our particular solution, is a copy of the exponential divided by the characteristic equation evaluated at I omega 1. It is I omega 1 there for alpha. So alpha is this complex frequency I omega 1. Remember, if you go back to the notes from Monday, you write the right-hand side as an exponential, the form e to the alpha t. Alpha is whatever's multiplied by the independent variable, which in this case is I omega 1. So if we play this out a little bit, P is right here. This is the characteristic polynomial. That would give you I omega 1 squared plus omega naught squared, which this then is e to the I omega 1t divided by I squared is negative 1. So this ends up being omega naught squared minus omega 1 squared. And so that is my complex solution. And then if you recall from Monday's class, if I want to find the real solution, that ends up being the real part of the complex solution. And the reason that it's the real part is because our complex forcing function here is the real part of the actual forcing function. So we recover the real part of this expression. Well, the only part that's imaginary is the complex term, and we already know that the real part of that complex term is cosine omega 1t. So this will simply be 1 over omega naught squared minus omega 1 squared cosine omega 1t. So this is the solution response to being pushed by something with frequency omega 1. And it makes sense that eventually, whatever your swing path is, if I continue to push you at a certain frequency, eventually you will look like the frequency with which I'm pushing you. So you can see here that the solution is cosine omega 1t, just like the forcing function is, but we have an altered amplitude. So I'm pushing you with an amplitude of 1, but based on whatever my frequency is, that amplitude becomes altered. And the question that we want to go with here immediately following this is, if I look at the response of the system as omega 1 approaches omega naught, what is happening to the amplitudes? So let me just remind you here that the solution is 1 over omega naught squared minus omega 1 squared cosine omega 1t, and the question that's being asked here is, what is the limit as omega 1 approaches omega naught of yp? Right? That's what we have to think about to answer this question. So I'll give you a second, commit to an answer. It should be pretty easy for you here, but then we'll talk about it together. All right, if you haven't paused and committed to an answer at this point, you should do so. So if I look at this, I have the limit as omega 1 approaches omega naught of cosine omega 1t over omega naught squared minus omega 1 squared. And if I evaluate this, then the numerator becomes cosine omega naught t, because omega 1 becomes omega naught. But then the amplitude, which is the denominator, 1 over the denominator, as omega 1 approaches omega naught squared minus omega 1 squared approaches 0. And it approaches 0 from the right, I'll say. So this is a positive number. It's 1 over a number approaching 0. We know that this approaches infinity. Now, all I want you to understand is this gets larger. The amplitude becomes unbounded as omega 1 approaches omega naught. And this is what we mean by resonance. That as we approach the natural frequency of the system, if I'm reinforcing the natural frequency of the system with an outside frequency of the same frequency, then we get this exponentially, it's not exponentially, linearly increasing, but infinite response. So the amplitudes get larger as the forcing frequency approaches the natural frequency. That's the moral of this example. However, what does it look like if they're actually equal? Not approaching, but actually equal to each other. And the reason I bring this up as a separate case is because if you look back at the work that we did here, the work that we did here assumed that they were different because I said that I omega 1 is not the same thing as I omega naught. But if we're in the case where omega 1 equals omega naught, which we are now, then this is the wrong analysis to do for that problem. So let omega naught equal omega 1, then consider that if we have z double prime plus omega naught squared z equal e to the I omega 1t, then I alpha, which is I omega 1, actually equals I omega naught, which is a root of the characteristic equation, which means we're in the case where P of alpha is 0. And so if you go back and look at your notes from Monday's class, then in the case where alpha, the characteristic equation at alpha is 0, in other words, alpha is a root of the homogeneous equation, then you're in case 2, which means that your solution ZP, this complex solution, it isn't the exponential divided by P of alpha, because P of alpha would be 0. It's actually T times the exponential divided by P prime at alpha. And so in this case, we would have T e to the I omega 1 T. The characteristic equation here is r squared plus omega naught squared. So its derivative would be 2r. So we have 2 times alpha, which is I omega 1. So this is, remember, if you're dividing by I, that's the same thing as multiplying by negative I. So this is negative I t over 2. And then e to the I omega 1 is cosine omega 1 t plus I sine omega 1 t. And remember, we're still taking the real part of this because this e to the I omega 1 t came from having a cosine on that right-hand side. So we're still going to look at the real part of this complex solution. And so if you look here, the real part of this complex solution isn't the cosine anymore. It's actually the sine, because if you take I times I squared is negative 1 times the negative that's already there. The real part of this turns out to be t over 2 sine omega 1 t. So what we have, if you look at our analysis above, is we're taking the limit of this solution in the omega naught equal omega 1 case. Omega naught does not equal omega 1. This is what you get. But somehow in the limit, when omega naught actually equals omega 1, we get this. So if omega naught is equal to omega 1, the response is given to us by the function t over 2 sine omega naught t, which is actually kind of incredible. What I want you to think about here for a second is what this thing looks like. It's a sine curve, but the amplitude of the sine curve involves time. So if you plot the graph of t over 2 and negative t over 2, then the response to this oscillation when omega naught equals omega 1 is you get sine, but it's trapped between these two values, but these two values go off to infinity. So this is what we call a time varying amplitude. This is resonance. You're in what's called the resonant state, because you end up with a unbounded amplitude as time increases. So if you have the exact same forcing frequency as you do natural frequency, this example shows that you will indeed achieve an unbounded response, which is known as resonance, or the resonant state. It's the maximal amplitude response. So in the absence of damping, we can actually get an unbounded infinite response. Now we'll look at a more appropriate model on Friday where we don't have, where we do have some form of damping. But here you can see our differential equation doesn't have a z prime term. It doesn't have a damping term. And so this is what we end up with. Now, what's very interesting here is somehow we just showed that if you're in the case where omega naught does not equal omega 1, but you let omega 1 approach omega naught, you wind up having this when omega 1 equals omega naught. And I feel like I left off something here. Oh, I left off my omega 1 that was down here, which would be an omega naught right here. Yeah, that looked weird to me. So there you go. If omega naught equals omega 1, you end up with this, which is what we have right here. So sorry about that. So we just showed both cases. We just showed this case here where they're not equal, but yet somehow in the limit, when you do get omega naught equal to omega 1, this turns into this. So the question is, how does that happen, right? So the question is, how does cosine omega 1t over omega naught squared minus omega 1 squared turn into t over 2 omega naught sine omega naught t as omega 1 approaches omega naught? Because if you simply just take the limit of this, you get an infinite amplitude, but it's a cosine function. It doesn't look like this sine. So where's this t over 2 omega naught? Where's all that coming from, right? Well, this requires you to recall something from Monday's lecture, and that is that you can take any part of the homogeneous solution and add it to a particular solution, and it's still a particular solution. So the scenario that we find ourselves in here is our particular solution, our response to the outside force is given by this function. But if you solve the homogeneous problem, so remember the differential equation here is y double prime plus omega naught squared y equal cosine omega 1t. That's our differential equation that gave these solutions. The roots of this thing are I omega naught, plus or minus I omega naught. So the homogeneous solution here is C1 cosine omega naught t plus C2 sine omega naught t. In the absence of damping, you just get a nice oscillation of frequency omega naught. That's why omega naught's known as the natural frequency. But here's the thing. I'm allowed to add any part of this homogeneous solution to the solution I have here. For any values of C1 and C2, I can add it to this, and it's still a particular solution. So it turns out that this solution that we derived isn't exactly what's giving us this in the limit. Turns out, we need to look at yp equal to, I've got 1 over omega naught squared minus omega 1 squared cosine omega 1t. But then I'm actually going to subtract from that. I think that's how I have it in here. Yeah, I'm going to subtract from that the exact same thing, cosine omega naught t. So understand, this was the original particular solution, yp. This is yp, I'll call it star. That was our original particular solution. YH, this is a part of YH. So our new particular solution we want to look at is the one we had minus this part of the homogeneous solution, where I make C1 equal to 1 over omega naught squared minus omega 1 squared. And if you do that, then you will get cosine omega 1t minus cosine omega naught t divided by omega naught squared minus omega 1 squared. And what's really cool here is, let's see if I can bring this all together. And what's really cool here is I can redo the limit now and get exactly what we proved it should be. Because if you take the limit as omega 1 approaches omega naught of this new particular solution, if you try to directly plug in omega 1 equal omega naught, notice that the top cancels and the bottom cancels. So you're in the 0 over 0 case, which should remind you of L'Hopital's rule. So we're going to apply L'Hopital's rule here to calculate the limit. And you need to be very careful here. A lot of students will mess this up. remember the way that you do L'Hopital's rule is you take the derivative of the top and the derivative of the bottom with respect to the variable that's moving. So the variable that's moving here is omega 1, so I've got to take the derivative with respect to omega 1 on both the top and the bottom. So the derivative, the only place where omega 1 appears on the top is right here. The derivative of cosine is minus sine. But then you have to take the derivative of the inside with respect to omega 1 because of chain rule, and that's where you get a t. Well, imagine that. A t of all things is what pops out there. And so carry over the limit here. And then in the denominator, the omega naught squared doesn't have an omega 1, so that's constant. That goes away. The derivative of this becomes minus 2 omega 1. And if you look, as omega 1 approaches omega naught, you get t over omega 1 becomes omega naught, and you get sine omega naught t, which is where this is coming from. Well, that's actually kind of cool, but what's even more important about it is an understanding of the journey that took place here. So this function here, this encapsulates what happens as a system with natural frequency omega naught is acted upon by an oscillation that has a frequency omega 1. So in other words, it's this function that we want to look at. And this function is a really, really important function. This is the function that gives rise to what's known as beats. So this is the function that gives us what's called the beats phenomenon. And to show you what's happening here with this function as omega naught approaches omega 1, I want to remind you of a pretty obscure formula from trig. I wouldn't necessarily expect that you remember this formula. But if we apply this formula to this function, we can write the following. We can say cosine omega 1 t minus cosine omega naught t is equal to 2 over, because I'm going to have omega naught squared minus omega 1 squared here. So it's going to be 2 over what we had, but then cosine omega 1 minus cosine omega naught. Omega 1 is b, omega naught is a, well, omega 1 t, omega naught t. So a minus b would be omega naught minus omega 1. So this would be, this would be sine omega naught minus omega 1 divided by 2 times t. Right? And then next would be adding them together would be omega naught plus omega 1 divided by 2. So you end up with actually 2 oscillations here. This thing is actually composed of 2 different oscillations. It has one oscillation that's kind of small because we're thinking of omega 1 and omega naught being close to each other. So if omega naught and omega 1 are close to each other, this is a very small frequency oscillation. And we think of this as being, well, honestly, if you just look at it, it's omega naught plus omega 1 divided by 2. This is what we call a mean frequency, which is the larger of the 2 frequencies here. This is the mean frequency oscillation, which is the larger of the 2. So you have a larger frequency, which means a faster vibrating oscillation here. And you have a smaller, much longer period oscillation that's happening here. This is best to view in Maple, so I want you to take a look at this with me here. Here's an example. So here we're taking a look at cosine 9x minus cosine 10x. It's very similar to what we just looked at. You can calculate these mean frequency, half difference frequencies, create the top envelope, which is the long curve, and the bottom envelope. So the 10 minus 9 over 2, that's the 1/2. That's the frequency of the long piece. So you've got the longer beat frequency here is what this is called. So the beat frequency in this problem is 1/2. And you've got this shorter rapid oscillation that's occurring in here. Now, if we were to just plot the curve, right? If we were to just plot the curve without the envelopes, you wouldn't. The envelopes aren't actually a part of this. You don't actually see those, right? So this is just the curve plotted. But there are actually, when you look at this graph, two oscillations. There's the rapid oscillation that's plotted, but then there's the outer oscillation that acts as a modulator for the amplitude of the signal. So that's where this two frequency behavior is coming in. Now, this is a very common thing in the real world. If you think about someone tuning a piano, what they'll do is they'll take like a tuning fork and they'll strike a key on the piano, and they'll hold the tuning fork next to the vibrating string, and if it produces a resonant effect, meaning it reinforces the vibration, you know that the two frequencies are very close together. But if they're not, then you can tell that there's this sort of beating that happens, which means you're not quite there yet. A lot of people will tune their guitars by looking for this what they call beat frequency, where they'll strum the guitar and they'll listen, and if it's kind of giving this sound, then that's sort of the beat happening, and it's not that perfect, clean, crisp frequency like they know they're supposed to have. I just want to show you an animation of this in play here. What I'm doing is looking at that exact kind of thing we were just talking about, which is cosine omega 1t minus cosine omega naught t over omega naught squared minus omega 1 squared. Here I have a playing the role of omega 1. So we're going to look at what happens as omega 1, or a, approaches the value, let's see, at 10.9. So I'm going a all the way up to 10.9, which is really close to 11. So let's see what happens here when we do this oscillation. So it starts out where you don't have any sort of definable pattern, but as we get closer and closer, the beats start to appear, and then all of a sudden we get that resonant state when we get really, really close. So this is, you see the beats start to appear, and as omega 1 gets closer to omega naught, the period of the beat, the period is this outer part here, that's one period of the beat. The period of the beat starts to elongate, and you end up in this resonant case. All right, let's go back to the analysis here, and then we're going to take a look at Maple for another couple of things here in just a second. So I want to name these frequencies because they turn out to be of critical importance for us. So the beat frequency, which we define with the letter delta, is equal to the small frequency. This is the beat frequency. It's the smaller one of the two. It's omega naught minus omega 1 divided by 2, and we do it in absolute value because we're not really considering negative frequencies here, at least not in this class. So we use the letter delta for that, which means that the beat period would be delta over 2 pi. So the beat period, the period of the beat is omega naught minus omega 1. Whoops, we got to take the inverse. So it would be 2 over that value. Now, both of these are in radians. These are circular frequencies. It's much more appropriate to look at this thing in hertz normally. So the beat frequency in hertz the hertz frequency, which I usually use a delta F for that. So this is the natural frequency or the beat frequency, excuse me. The reason it's in hertz is this is in, like, say, radians per second. Then you divide by 2 pi, you cancel out the radians part, and you just leave cycles per second, which is hertz. So it's the exact same value as before, but we divide by 2 pi, so it's really dividing by 4 pi. So this would be the beat frequency in units of hertz, which means that the beat period in units of hertz would be 4 pi over this amount here. And the other one is called the mean frequency. It's really easy to remember because it's, mean or average. So the mean frequency is omega naught. You don't need absolute values here because everything's positive. Omega naught plus omega 1 divided by 2. And the mean frequency, and we usually use omega with a bar over it for that. Anytime you put a bar over a variable in mathematics, that means you're taking the average of it. So I'm taking the average frequency here. So the mean frequency in hertz would be omega naught plus omega 1 divided by 2 pi, which would give me 4 pi. So that's the mean frequency in hertz, and the notation I would use for that is bar sub f for that. So it's important that we know these basic formulas for calculating beat frequency and mean frequency. I'll do a couple of examples with you to kind of show this off. So the first example is this. Determine the approximate period of 1 beat for this equation. So I'm looking at this equation, and omega naught is the square root of 11. Omega 1 is 3. So I'm looking for the period of 1 beat. So I usually do everything in terms of hertz. So I need the beat frequency first, right? The beat frequency is absolute value of square root 11 minus 3 divided by 4 pi. That's the beat frequency. We can calculate that here in just a second. And then the reciprocal of that is the beat period, which is what we want to know for this problem. So I could just directly calculate this if I wanted to, but I wanted to show you both of these. Okay, so get my calculation out here. I have it over on the Maple file. We'll get to the Maple file here in just a second. All right, so let's see here. If you take, well, it looks like I didn't have it on the Maple file. All right, so let me do that real quick. So I'm just going to take and calculate each of these real quick. All right, so this gives me a beat frequency of 0.0252. And this gives me an approximate period of 39.689. So this is almost 40, right? So approximately 40. 40 seconds is the beat period there. So it's how long it takes for 1 beat if this were in terms of seconds. Then this would be 0.0252. This would be how many cycles per second that the beat would achieve. So this is the beat, right? That's what we're talking about here. That's the outer envelope oscillation. All right, so if you put 40 for the answer, congratulations, that is correct. Let's take a look at it in Maple real quick. All right, so you can see here I have the differential equation that we're looking at. I'm looking at it under initial conditions 0, so I could get the response. So the response looks like this guy here. Make this a little bit bigger for you. And you can see I went in and calculated the beat frequency, and then I took the reciprocal here to get the beat period. And you can see the graph bears it out, right? Because if you look at this envelope, the envelope completes one oscillation in about 40 seconds, just under 39.689. So that's what we just calculated was the beat period, or the period of this envelope to the rapid frequencies that are occurring here. All right, let's do another similar example here, but we're going to calculate something slightly different. I want to determine the approximate number of rapid oscillations. So the thing that's actually graphed, how many rapid oscillations occur during one beat period, right? During a full beat period, how many rapid oscillations occur for this particular differential equation. And we know that this is probably going to be a beat because we know omega naught is 3, omega 1 is pi. And so we're in the case where omega naught is approximately, they're close to each other, so we know that beats will occur here. All right, so go ahead, pause the video here, give it a try, see if you can come up with the correct answer, and then we'll take a look at it together. All right, if you haven't paused the video yet, you should go ahead and do that. So let's take a look at it here. I need to find the number of rapid oscillations in one beat. So I need to find the beat period first, and then I need to find the rapid oscillation frequency, and then I need to multiply the two together, right? So one beat occurs in approximately 4 pi divided by, I have to subtract the two oscillations. So we'll get that number here in just a second. And then I have to look at the rapid oscillation frequency. So the rapid oscillation frequency is omega bar sub f, which would be pi plus 3 divided by 4 pi. Yes. And so I need to get that value real quick as well. All right, I'm going to do these off to the side once again real quick. All right, so the rapid oscillation frequency here will be 0.4887, and since it's rapid oscillations, this is Hertz frequency, so this is cycles or oscillations per unit time. I'll just assume seconds here. And then I'm also going to do it for the beat period. The beat period here turns out to be, I don't quite have it. Okay, so the beat period here turns out to be 88.75, and this is in terms of seconds, right? So it's the amount of time it takes for the beat to complete one full cycle. So it has a beat period of 88 seconds, okay? Well, if you can complete one beat in 88 seconds and you're oscillating at a frequency of 0.488 cycles per second, if you multiply these two things together, it'll give you the number of cycles, which is the number of rapid oscillations. So the number of rapid oscillations is 88.75 times 0.4887, which turns out to be 43.375 oscillations or cycles. So we would expect this oscillator to oscillate back and forth across equilibrium 44 times in one beat. So it's a very rapid oscillation. If you've ever heard a dial tone, it sounds a lot like a dial tone, but it's like this, you hear the tone, but behind it's this really rapid oscillation that's going on. If we look at this in Maple, you'll see that we are in fact correct. It is 44 for the answer. So in Maple, I have taken, here's the oscillation we just looked at right here. I've taken this particular problem and looked at it on the interval from 0 to 100 here, so I can get everything fit in. And you can see that the period is indeed about 88. It's just short of, there's 90, it's just short of 90. And we're going to count the number of oscillations. Now, the easiest way to do this is count peaks, and you may be a little bit off here, but we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Probably don't count that one. 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43 if we count those, which is kind of where we are. Do we count this one? Like, we're right on the number, which is 43.37. So all of this makes sense given the graph that we're looking at here, which is the solution to that differential equation. Now, I didn't do it at an initial condition of 0 here. I did an initial condition of 1, but it doesn't matter what the initial conditions are because that dies off rapidly. But once you're into a beat state, you're going to get this many rapid oscillations per period. All right, so examples like these two that we've just done, where you have to calculate the beat frequency, the beat period, the number of rapid oscillations. These kinds of problems are fair game for the quiz on Friday, so make sure that you're taking a look at that material. The last thing I want to do is kind of do this in reverse. I'm going to give you the graph, see if you can tell me which differential equation it came from. So I have some sort of harmonic oscillator here, which is demonstrating a beat pattern. I can see that I've got an outside oscillation and I've got an inner faster oscillation. So I know I have a beat, I know I'm in the beat case, which means that omega naught is approximately omega 1 and there's no damping. We don't talk about beats in the case where there's damping. All of our problems today have included no damping. So I can't include A because it doesn't have a forcing term. I can't include B because it has no damping, or because it does have damping, so I don't have a beat state possible. Same thing is true for C. There's no beat state possible because there's damping there. So it comes down to D or E as being the only possible choices. I'm going to let you take a look at it and see if you can narrow it down further. All right, if you haven't done so already, pause it, commit to an answer, either D or E here, and let's take a look at it. So I'm going to analyze each one. For D, omega naught is the square root of 7, and omega 1 is 3. So I'm going to try to look at the beat period. To me, that's the easiest one to see. So whichever one has a beat period that's closest to 40 is going to be our winner here. So the beat period, the period of the beats, I always do the Hertz one, but it's 4 pi over, let's see here, omega naught minus omega 1 in absolute value. All right, so we've got that one. I'm going to calculate these off to the side. All right, so this one is I'm getting 35.47 for that one. And then this one, the frequency here is square root 5. The forcing function frequency is 2. So the period of the beat here I'm getting 53.23. And that's much too big. So out of the two of these, the only one that's even close, the only one that we could make a case for is 35.47. And I think that's probably right, because if you look at where this peak is here, this peak looks like it's matching. So 1, 2, 3, 4, 2, 3, 4. Yeah. This peak looks like it's matching this peak right here. And they're approximately 35.47 apart. Okay? So the correct answer here would be D. Okay, let's look at example 4. Example 4, we're looking at some sort of oscillation that picks up and increases in intensity over time. I want you to tell me which of these correctly is a differential equation that could give a response like this. All right, so I'll ask you to pause the video here, see what you come up with, and then we'll talk about it together. All right, if you haven't paused the video yet, please do so. What we have here is a resonant state. You can see the linearly increasing amplitude. A resonant state only comes from omega naught being equal to omega 1 where there is no damping. So that's what we're looking for here. You've got to have a forcing function, so B is out. Here, omega naught is square root of 3, which is not the same as omega 1, which is 3. They're kind of close. This would probably lead to beats, but it doesn't lead to resonance. So that one's out. We have damping on C and D, so those are out. E is square root of 5, which is approximately 2. But once again, they're not the same, so this is beats. F is correct because omega naught is 3, which is actually equal to omega 1, which is also 3, so that's my resonance state. So the only oscillator equation that can produce a response like this is F. All right, so just as a quick recap, what you need to get out of this lecture is a complete understanding of how we transition from a natural undamped frequency to, once you start to force it, you create this beat state. And then if you push it all the way to the point where the driving frequency or the forcing frequency matches the natural frequency, you produce this resonant state. So you need an understanding of those 3 different states that we're in: the state without forcing, the state where beats occur, and then the state where resonance occur. You need to understand the transition between those states and how to calculate the different values associated with the beat period, beat frequency, rapid oscillations, etc. All of this information is going to play a heavy part in Exam 3. It plays a heavy part in what we're going to talk about on Friday. It plays a heavy part in your 3rd project. This is a big part, or a big thing to understand about some of the applications that are ahead. All right, enjoyed talking to you about this today. This is one of my, I like this topic a lot. It's a very rich topic. If we were in class, I'd have some stuff I'd try to demonstrate to you, but we're doing the best we can. I hope y'all are all doing well out there. I'll talk to you again on Friday. Have a good day.